Hey folks, how y'all doing? Hope you're doing well. This is it. This is our last day together. We're covering section 6.5, least squares approximations. Let's get started. All right. So way back in chapter 1, we saw that the matrix equation ax equals b may have no solutions, can have one solution, can have an infinite number of solutions. So suppose that we have a system where the system has no solutions, but the columns of A are linearly independent. Then can we find a vector that is closer to being a solution than any other vector? In other words, can we find the best possible approximation to the solution? So closer to being a solution is the nearest possible approximation. So that's their goal for today is, what if we can't solve a system of equations? Can we find the best possible approximation? So what we mean then is that the vector v, when we plug it in, a times v won't equal b, but the magnitude of av minus b is the smallest possible. And so here's our definition. A least squares approximation is a vector such that if w is any other vector, the difference between av and b is less than the difference between aw and b. Probably not necessary to use this complexity of the definition. But the idea is that we want av to be as close to b as possible. We want these two things to be as close as we can get. Okay. All right. So if ax equals b does not have a solution, then the equation always has at least one least squares approximation. And if the columns of A are linearly independent, then the equation has a unique least squares approximation. Then there's only one. So we have this theorem. We can always find a least squares approximation, and if the columns are linearly independent, in fact, there's only one least squares approximation. Okay? So here's how we find it. We have the equation ax equals b. We already know that it has no solution. What we're going to do is we're going to multiply both sides by the transpose of A. So A transpose on the left side and A transpose on the right side. And solving that equation gives us the least squares approximation. That's the process. We have a system, it doesn't have a solution. We can multiply both sides by A transpose, and then we do get a solution. That will be our least squares approximation. So I'm going to do a couple of examples, and then we'll talk about why this works. So let's try this one here. Find least squares approximation to these equations. So first of all, this system has no solutions. So first of all, this system has no solutions. The top row says that 4 times x equals 2, which would say x is 1/2. The middle row says that 2y is equal to 0, so y would be 0. but then 1 times 1/2 plus 1 times 0 doesn't add up to 11. And so just looking at these three equations, 4x equals 2, 2y is equal to 0, x plus y equals 11, it's clear that we cannot solve all three of those equations. All right, so since we know that there is no solution right now, we're going to multiply both sides by the transpose. So the left side, we'll get 401021 times 400211 times x. On the right side, we'll get 401021 times 2011. To solve the left side, we apply the column row rule. So we're going to pair up 40 the column with 40 the row, 02 the column and 02 the row, and 11 the column and 11 the row. So that's 16000 plus 0004 plus 1111. And that adds up to 17115. So let's try the right side. This is just a linear combination. It's just 2 times the first column and 0 times the second column and 11 times the third column. So that's 80 plus 00 plus 1111, which is 1911. All right, so our last step is we want to solve this system 17, 1, 19, 1, 5, 11. Okay. All right. Oh, let's see. We can switch rows. So that would give us 1, 5, 11 on the top row, 17, 1, 19 on the bottom row. So switching rows. And then I want to get rid of this 17. So row 2 minus 17 row 1. These numbers are going to get a little hairy for a second, but they will work out really nicely in a moment. 17 minus 17 is 0. 1 minus 85 is negative 84. And 19 minus 187 is negative 168. Then we'll take row 2, divide that by negative 84. And we get 0, 1, 2. Like I said, that works out pretty nicely in the end. And then row 1 minus 5 row 2. We get 1, 0, 1, 5 minus 5, and 11 minus 10. And 0, 1, 2. And so this vector, so our least squares approximation, we use this little hat symbol to indicate that we're looking at an approximation, is the vector 1, 2. This should work exactly in this system. 17 times 1 plus 1 times 2 does add up to 19. 1 times 1 plus 5 times 2 is 1 plus 10. That adds up to 11. It works exactly in this system, but it only works approximately in the original system. Okay? So this is our least squares approximation. All right? Let's try another example. Let's find a least squares approximation to the inconsistent system whose augmented matrix is this matrix right here. So we'll have to solve on two sides. On the left side, we get the transpose 1, 2, -1, 8, -2, 1 times 1, 2, -1, 8, -2, 1. One case going across, one case going down. We're going to apply the column row rule again. And we get 1, 8 times 1, 8. 2, -2 times 2, -2. And -1, 1 times -1, 1. So 1, 8 times 1 is 1, 8. 1, 8 times 8 is 864. 2, -2 times 2 is 4, -4. 2, -2 times -2 is -4, +4. And finally, -1, 1 times -1 is 1, -1. -1, 1 times 1 is -1, 1. So we get 1 plus 4 plus 1 is 6. 8 minus 4 minus 1 is 3. 8 minus 4 minus 1 is also 3. 64 plus 4 plus 1 is 69 times x. All right, on the right side, we multiply AT times the right column. So 1, 2, -1, 8, -2, +1 times 3, 2, 5. That's a linear combination. We just multiply this out. The first column gets a weight of 3. The second column gets a weight of 2. And the last column gets a weight of 5. So we have 324 plus 4, -4 plus -5, +5. In the top row, we get 2. 7 minus 5 is 2. In the bottom row, 24 minus 4 is 20. 20 plus 5 is 25. And so we have to solve this system. 6, 3, augment that with a 2. 369, augment that with a 25. All right. So let's try this. I'm going to switch the two rows again. 369, 25, 6, 3, and 2. I'm going to take row 2 minus 2 times row 1. So 6 minus 6 is 0. 3 minus 138 is -135. And 2 minus 50 is -48. Let me just check that. Okay. All right. Oh, let's see. So when we divide this through, we get row 2 divided by -135 is 0. Let's see. That's going to be 1. And 48 divided by 135, I can take out a 3, and we get 16 over 45. All right, let's keep going. Row 1 divided by 3 gives us 1 and 23 and 25 thirds. All right. And then finally, we're going to get row 1 minus 23 row 2. So that's going to be 1, 0. And what we're going to have up here is 25 over 3 minus 23 times 16 over 45. I'll have to simplify that in a moment. All right, so 23 times 16. Let's see, 3 times 6 is 18. That's going to be 138. 23 times 1 is 23. We get 368. And then 25 over 3, if we multiply by 15, that's going to be 5 times 5 is 25. 275. And so we get 275 minus 368 is going to be negative 93. So this last column is negative 93 over 45 and 16 over 45. Oh, and that's an ugly number. I hope I did this right. But we'll move on. All right. Let's move on. So why does this work? So I have some columns here where we're looking at AX equals B. And let's say these are columns V1 and V2. And over here is B. And B is not a linear combination of V1 and V2. That is V1 and V2 over here generate a plane, and B is not on that plane, for example. But I can project B onto the plane, and this vector here is in the plane. And therefore, the projection does equal AX for some input vector X. But that means that the vector from B to P is orthogonal to the plane. So this is a little tricky. This says that the vector that goes from B to P is orthogonal to the column space of A. But we saw back in chapter 4 that the set of vectors that's orthogonal to the column space of A is the null space of A transpose. And therefore, A transpose times B minus P is going to be 0. Well, all right. Since P could be written as A times X, then A transpose times B minus AX is equal to 0. Distribute the AT, A transpose times B minus A transpose times AX is equal to 0. And then put these on two separate sides. And this gives us the equation that we just saw. Multiply AX times AT on the left and multiply B times AT on the right. And so this uses that weird fact that we saw in chapter 4 that the column space of a matrix and the null space of the transpose are always perpendicular to each other. We're finally getting a use for that. It gives us this method for finding least squares approximations. All right. So we have a couple of minutes left. Let's just try a couple of true-false questions from this chapter, and we'll wrap up. Is it true that every orthonormal set of vectors is linearly independent? I'll pause in case you want to think about it. This is true. All orthogonal sets are linearly independent. Except if they contain the zero vector. We have that as a fact. But the zero vector cannot be made into a unit vector. Cannot be scaled to a unit vector because it requires dividing by the magnitude, and the magnitude is 0 in this case. And so since the zero vector cannot be scaled to a unit vector, so the zero vector can't be in an orthonormal set. And so every orthonormal set is linearly independent, and that is true. All right. Let's move on to the next one. Every non-zero subspace of Rn has an orthogonal basis. True or false? Yes, true. Every non-zero subspace has a basis. We saw that way back in chapter 3. And every basis can be converted to an orthogonal basis. This is what we did last time, chapter 6, the Gram-Schmidt process. So this is a true statement because every non-zero subspace has a basis, and every basis can be converted to an orthogonal basis. And therefore, every non-zero subspace has an orthogonal basis. So that is a true statement. We'll do one more. Let's look at W is span of V1, V2. It's a subspace of R3. And the projection of U is equal to 0. Then U itself is equal to 0. This is false. So let me show you what's going on here. I have a span of two vectors. Two vectors will span a plane. The vector U could be pointing exactly straight up right on the plane, and when we project it straight down, the projection is just a single point because the vector U is exactly perpendicular to the plane, so the projection just lands to be a single point. So the projection of U onto W is the zero vector, but U itself is not the zero vector. So this is not necessarily true. Let's keep going. Number 4. If the columns of a matrix A form an orthogonal set, then A is invertible. So if the columns of A form an orthogonal set, then A is invertible. This is true unless one of those columns is 0. We know that all orthogonal sets are linearly independent unless they contain 0. That do not contain the 0 vector are linearly independent. And you know what? There's an even better reason this is false. Okay. That's okay. We'll go ahead and end this. Discard. Okay. Um, hmm.
Hey folks, how y'all doing? It's a little cold in here today, but we have one more section to cover before you finish up chapter 6. Actually, a solution. All right, times 1/8 plus times out negative, and the minus 20 plus 5 is 25. All right, so this is 1 plus 4 is 5, 5 plus 1 is 6. 8 minus 4 is 4, minus 1 is 3. 8 minus 4 minus 1 is 3 again. 64 and 4 is 68, and 1 is 69. Oh, wow. 5, get rid of 6 is 0. 8, 5, right. This looks like fun. All right, divide by 135, and we get 48 over 135. I can take out a 3, and I get 16 over 45. All right. let's try this. Get rid of this 69 here. So row 1 minus 69 row 2 is going to give me 3, 0, and then this last term is going to be 25 minus 69 times 16 over 45. 69 times 16 is going to be 1004. So that's 25 minus 1004 over 45. It's got a common denominator here. 25
Okay, yeah.
times 45 is 825 plus 300 is 1125.
Okay, I'm going to get out. Let's try this one more time. All right. Hi, folks. How y'all doing? This is our last video. We're covering section 6.5. Let's go ahead and get started. So way back in chapter 1, we saw that the matrix equation, AX equals B, can have 0 solutions, 1 solution, or an infinite number of solutions. We're going to talk today about the case where it has 0 solutions. Suppose we have a matrix and AX equals B has no solutions, even though the columns of A are linearly independent. Can we find a vector V in Rn which is closer to being a solution than any other vector in Rn? In other words, is it possible to find some vector that, even though it's not an exact solution, is the very best approximation that we can get for that? So what we mean is that whatever vector this is, V, when I multiply this times A times Z won't equal B, but the magnitude of the difference between the two vectors is as small as possible. So this is our definition. We call this a least squares approximation. A least squares approximation to AX equals B is some vector such that if W is any other vector, then the difference between AV minus B has a smaller magnitude than the difference between AW and B. That's the definition, the requirement that we have to have. All right. If AX equals B does not have a solution, then we're guaranteed that the equation always has at least one least squares approximation. And furthermore, if the columns of A are linearly independent, then the least squares approximation we get is unique, that there's only one. So we always have a least squares approximation. And if the columns are linearly independent, in fact, we have a specific unique least squares approximation that this one approximation is better than any other. All right, here's the process for finding the least squares approximation. Suppose that we know that AX equals B has no solution. Then solving the equation, AT times AX equals ATB, gives us a least squares approximation. Now, there is also a calculus-based technique where you take the magnitude of AX minus B, and then you minimize that magnitude. You take the derivative, you set the derivative equal to 0, and then you solve to find the vector x that minimizes that distance. This is a non-calculus based solution that just uses working with matrices. Multiply both sides of the system by a times t, a transpose, and that gives us the least squares approximation. So on the next slide, we're going to do an example, and then we'll talk a little bit about why does multiplying by the transpose actually do this for us, and we'll see why that works. Okay? All right. So here's the example we're going to work through. Find the least squares approximation to these equations. So first of all, I want to mention that these equations don't have a direct solution. The top equation says that 4x is equal to 2, and the second equation says that 2y is equal to 0, and the third equation says x plus y is equal to 11. Well, if 4x is equal to 2, that would make x equal to 1/2, and if y is equal to 0, that's y equals 0, and 1/2 plus 0 definitely doesn't equal 11, and so I cannot make all three of these equations true, and so there is no solution. But there will be an approximation to the solution, the best approximation that we can get, and so let's talk about how to do that. Whoops, let me go back, sorry. There we go, trying to do that. So on the left side, we're going to multiply by A transpose. So we'll get the matrix 4, 0, 1, 0, 2, 1 times 4, 0, 0, 2, 1, 1. And we can solve that side by the column row rule. And so we're pairing up the column 4, 0 and the row 4, 0, then the column 0, 2, and then the row 0, 2, and then finally the column 1, 1, and the row 1, 1. All right. So 4, 0 times 4 is 16, 0. And 4, 0 times 0 is 0, 0. 0, 2 times 0 is 0, 0. And 0, 2 times 2 is 0, 4. And finally, 1, 1 times 1 and 1, 1 times 1. And when we add all these together, we get 17, 1, 1, 5. All right. That's the left side. Now on the right side, we have to multiply the transpose of A, 4, 0, 2, 4, 0, 1, 0, 2, 1, times the column vector 2, 0, 11. So this is just a linear combination where these are the weights. So I'll weight the first column by 2, the second column by 0, and the third column by 11. And that is 8, 0. I'll skip the middle one because it's 0, plus 11, 11. And that turns out to be 19, 11. And so we now solve this new system, 17, 1, 1, 5, augmented with 19, 11. All right. So if I solve this, first thing I might want to do is switch to 2 rows. And now I'd like to get rid of this 17. And the numbers are temporarily going to be kind of messy. but they'll work out nicely in a moment. 1, 5, 11. 17 minus 17 is 0. 1 minus 85 is negative 84. And 19 minus 187 is negative 168. So if we take row 2 divided by negative 84, we get 0, 1, and 2, and we're back in the realm of kind of nice numbers again. And then finally, row 1 minus 5 row 2. 5 minus 5 is 0. 11 minus 10 is 1. And so we get this solution vector. So our approximate x is the vector 1, 2. All right. This vector will be an exact solution to this system. We can check that. 17 times 1 plus 2 adds up to 19. And 1 plus 2 times 5 is 1 plus 10, which is 11. It will be an exact solution to that system, but it will only be an approximate solution to this system. All right. But we found the least squares approximation. Let's try another example. Let's find the least squares approximation to this system. We're told that the augmented matrix is given here. So we have some calculations to work on both sides. On the left side, we multiply the transpose 1, 2, negative 1, 8, negative 2, positive 1, times 1, 8, 2, negative 2, negative 1, 1. And that's going to be the coefficient of x. Once again, we'll apply the column row rule. And the columns and the rows we get always match up. It's 1, 8 times 1, 8. And then the column 2, negative 2 times the row 2, negative 2. And finally, the column negative 1, 1 times the row negative 1, 1. So 1, 8 times 1 is still 1, 8. 1, 8 times 8 is 864. 2, negative 2 times 2 is 4, negative 4. 2, negative 2 times negative 2 is negative 4, positive 4. And then negative 1, 1 times negative 1, and negative 1, 1 times positive 1. And when we add all this together, we get 6, 3, 3, 69. All right. So now let's look at the right side. On the right side, we also multiply by A transpose. That's 1, 2, negative 1, 8, negative 2, positive 1. But the right side is just a column 3, 2, 5. And this is just the coefficients of a linear transformation. 3 times 1, 8, plus 2 times 2, negative 2, plus 5 times negative 1, 1. And that is, in the top row, we get 3 plus 4 is 7. 7 minus 5 is 2. In the bottom row, we get 24 minus 4 is 20. 20 plus 5 is 25. And so to finish up, we want to solve this system. 6, 3, 2, 3, 69, 25. All right. Again, I'm going to try switching the two rows. So I have a 3, 69, 25 on the top row and 6, 3, 2 on the bottom row. And then I'll take row 2 minus 2 times row 1. All right, so 6 minus 6 is 0. Uh, 3 minus 138 is negative 135, and 2 minus 50 is negative 48. All right, we'll take row 2, divide this by negative 135, and we get 369 and 25, 0, 1, and 48 over 135 reduces to 16 over 45. So we're going to get a little bit of a fraction here, but that's okay. We can muddle through. And now I want to get rid of this 69. So row 1 minus 69, row 2. We get 3 and 0. 25 minus 69 times 16 over 45. So that's the calculation we're doing. 29 minus 69 times 16 over 45. I have done this calculation before. It turns out to be 21 over 45. But you can check this. And then finally, we're going to take the top row and divide it by 3. So we get 1, 0, and then we only get 7 over 45, and 0, 1, and 16 over 45. And so our approximate vector x is 7 over 45 and 16 over 45. This will not be an exact solution to the system, but it turns out to be the best approximation we can get. It is as close as we can get to being a solution. All right. So let's move on. So let's talk about why this works. What we know is that we have this system, AX equals B, where B is over here, A, which has maybe some columns, say V1 and V2, is over here, and it has no solution. That means that B cannot be written as a combination of V1 and V2, which means B is not in this plane that V1 and V2 generate. But I can project B onto the plane, and that projection is a linear combination, which means that P is going to equal to A times X for some input vector X. This will be a solution. We can solve for the projection, but we can't solve for B itself. So now what we're going to do is we're going to look at the difference vector between B and P. This vector is at a right angle to the plane. So the vector B minus P is perpendicular to the span of V1 and V2. But the span of V1 and V2 is the column space of A. And here's where we use something surprising. We saw in chapter 4 that any vector that is perpendicular to the column space of A the perpendicular space to the column space of A is the null space of A transpose. So we use this factor. This was in chapter 4. That the orthogonal complement, the perpendicular space to the column space of a matrix, is the null space of the transpose of the matrix. And that means that if I take A transpose times B minus P, the answer is going to be 0 because it's in the null space. It's the solution to the homogeneous equation. And so that gives us this equation here. And now I'm going to just do some algebra. I'm going to, since P is a linear combination of A and X, I'm going to go ahead and replace P with AX. And then distribute the AT in this equation. So AT minus B is equal to AT minus AX. And then put one of these terms on each side of the equation. So AT times AX equals AT times B. And that is what we've been doing, taking the equation that has no solution and multiplying on the left by the transpose and multiplying on the right by the transpose. It works because of this trick that the column space of A and the null space of the transpose are always at right angles to each other. All right. So that wraps up least squares approximations. We've got a little bit of time. Let's just practice some true-false questions before we move on and see how this goes. So let's look at this true-false question. Every orthonormal set of vectors is linearly independent. If you want to think about this for a second, pause the video. This is true. We have a couple of facts here. Every orthogonal set of vectors is linearly independent. Unless it contains the zero vector. But an orthonormal set cannot contain 0 because the 0 vector is not a unit vector. Orthonormal sets only contain unit vectors. And therefore, an orthonormal set doesn't contain the 0 vector, and therefore it is linearly independent. This is always true. Let's move on. Let's try this one. Is it true or false? Every non-zero subspace of Rn has an orthogonal basis. This is also true. In chapter 3, we learned that every non-zero subspace of Rn has a basis. Doesn't say anything about it being orthogonal, it just says every non-zero subspace has a basis. Whoops, let me go back down here. Try that. Trying to get my camera back on. Every non-zero subspace of Rn has a basis. And just yesterday, or in the last video, we learned that every basis can be made into an orthogonal basis. This was called the Gram-Schmidt process. And so combining these two pieces of information, if every non-zero subspace has a basis and every basis can be made orthogonal, then every non-zero subspace does have an orthogonal basis. We can do this every single time. All right. Two more. If W is the span of two vectors in R3 and the projection of U onto that subspace is 0, then U itself is 0. This is false. So let's draw an illustration and explain what's going on here. So I have these two vectors, V1 and V2. Their span is some plane. Okay? But what if U is exactly perpendicular to the plane? So that when we project U onto the plane, the shadow it casts is just a dot. Then the projection of U onto the plane is equal to 0, but U is not 0. U just has to be perpendicular to the plane. So that's a diagram explaining what happens, but we have a formula that the projection of U onto W is the dot product of U and V1, V1, and V1, plus U and V2, 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 V2. If U is perpendicular to the plane, then this dot product will be 0, and this dot product will be 0. And so the projection will be the 0 vector. So all we need is for U to be perpendicular to the plane. We don't need for U to be the 0 vector. All right. Last one. If the columns of a matrix A form an orthogonal set, then A is invertible. This is false. If we have an orthogonal set, it doesn't have to be square. A might not be square. And we have to be square to be invertible. And so that's a false statement. All right. Well, thanks for bearing with me this summer. We will begin reviewing for the final exam. And good luck. Let me know if you have any questions. Y'all take care. Bye-bye.